This is Mateen Jangda, and this is our CS 2316 final project with Krishna Maran. This project analyzes the NFL statistics and fantasy football statistics for every player who has played in the NFL over the last 2.5 years, from the start of the 2019 season to halfway through the current season. We defensive ranks versus each position for the 2019 season from the NFL fantasy website. We did this by getting the URL, then getting the HTML content from that website, and parsing that data, putting all that the data that we wanted for each player into a list. That list gave us the ranks for the defense against the QB for the 2019 season, and we put this as QB1. We did the same thing for the running backs for the 2019 season, different extension but same website. For the running backs, exact same thing for the wide receivers, all with the same data with the defense, how they perform against that specific position, and how much the defense would allow that game on average. We did the same thing for the tight ends for the 2019 season defense. For 2020, we use API rather than HTML, so we requested this converted to JSON and used a dictionary format to get the data that we wanted. So we got the team, the fantasy points allowed, and the rank for each position: quarterback, wide receiver, running back, and tight end for the 2020 season. The 2021 season was similar to the 2019 season, where we got the data from a HTML source. We got all our data for each position, defense versus each position, from CBS Sports. This was all, once again, same thing, teams, the ranks, and how much the defense would be expected to allow per that position. And this was done for running backs, wide receivers, and tight ends for the 2021 season. This data then was, we had to get data for the 2019 season, 2020 season, 2021 season, on the ranks for each position, on how the QB, wide receiver, running back, tight end are projected to do for that season, and where they're ranked, and how many points they will be expected to let up. So we got our QB data from Washington Post, parsed that data to get the quarterbacks for 1 through 32. Put this, then we added a couple quarterbacks: Derek Carr, Nick Foles, Marcus Mariota, and Kyler Murray. Ranked those how they were expected to do. We did the same thing for wide receivers, got that data from Washington Post, and we put this data together, parsed it, and we did the same format on how the wide receivers expect, how many points they're expected to put up, and where they're ranked compared to their peers in that position. Tight end was the exact same website, parsed using Beautiful Soup. Running back for 2019 also done the same. For 2020, exact same way we did it, but we used the ESPN website, and we did this through Beautiful Soup. Got the same content, but for the 2020 season, running backs, wide receivers, tight ends, all from the same website for 2020. 2021 ranks for that offensive position we got through Sporting News. The links were a little different, so the extensions had to change for each position, but almost the exact same method. We just had to add a couple players: AJ Brown, DJ Moore for the wide receivers, and then TJ Hawkinson for the tight ends for the 2021 season. We then cleaned the data frame that we got starting from the 2019 to 2021 season. We just had to drop a bunch of columns that were useless for us and for analysis. We then just had to add positions for each player. We then had to add a couple columns. One of the columns was defensive points allowed, so how many points that the defense allows per that position. This was using the data that we did in the first 12 entrances. So we had QB1 through QB3. Those were how much like the defense allows and what the defensive rank is. So we added those for 2020, 2019, and then 2021. Then we added how much the offense is expected, their expected fantasy points and their ranks, and this was through that second set of data sets that we got for 2019 to 2021. And these were FPT/G and rank, and we put these in for 2019, 2020, and 2021. We then had to take out the NaN value. So let's say QB, running back, or wide receiver 10 was not in that list or rankings that we had. So then we had to give them expected fantasy points and ranks based off what we thought. And these ranks were one extra than what we had in our rankings. So we did 1 through 32 for the rankings. So that any QB that wasn't in that rankings list was 32. The running backs that were in the list were 66. Wide receivers were 65. And the tight ends were 17. And then we gave them these ambiguous, kind of calculated expected values, 8.75, 4, 5, and 3 for their respective positions. We added percent change also. So this was using a formula to calculate how we would create this percent change. So how the player does based off how much the defense allows. Then we added the last column that we added was the environmentals, which was using whether it was the roofing, so the indoors or outdoors, what type of grass, turf, or astroturf it was, temperature within its ranges, and then wind speeds. And then this was all summed up into a column for environment. And then we had our final CSV file or final data frame with all the columns.
Now we'll move on to analyzing the data. So for our first insight, we decided to compare the defensive rank to how each player performed based on their projected fantasy points for each game. So the D rank column ranges for 1 to 32 for all the teams, and the FPT over G minus the total column is the percent error of the expected fantasy points versus the actual fantasy points scored. So a positive value means the player overplayed their projection, and a negative value is the opposite. So if a player was facing a defensive rank that was lower, aka a higher number, we hypothesized they would be able to overplay their projection. This is important because based on the trends from this table, we can determine when the players will play their best from what defensive rank team they're facing that week. In the next insight, we examined the points allowed on average by the defense per position to the average fantasy points scored for each player. So the DFPT allow column is the average fantasy points allowed for each position based on the defensive team and the season, and the total DKP is the average fantasy points scored. And we showed this data for only players that played more than 5 games, so that the data wouldn't be as randomized for players that just played 1 game and had a good game. This is important because we can determine when players will be able to play their best from how many fantasy points the opposing defense allows in their position on average. For Insight 3, we were examining the average passing yards per game for quarterbacks who played more than 20 games to the environment rating we created based on the wind speed, temperature, surface, and roof. So the pass yards column is the average passing yards for each QB for each game, and then the environment column adds up the ratings from the 4 factors from the formula that Mateen explained earlier. And we only included the QBs that only played more than 20 games, and we used the game count column for that. This is important because we can determine how much and how effectively the QBs will throw the ball with certain environmental conditions before a game. For Insight 4, we were comparing the average fantasy points per game for every player to the new expected fantasy points per game that we created with our own formula from the code in Phase 2. So the new EXP column is the new expected value, and it's based on the actual expected fantasy points per game, the actual fantasy points scored, and the points allowed on average by the defense they are playing. This is important because we want to see how accurate our new expected values actually were to the real fantasy points scored on average for each player, to see if our expected value could accurately predict the scores. For Insight 5, we were comparing the maximum fantasy points scored for each position for each team during each year to the average points allowed by the defense for each position for each team during each year, and the defensive rank of each position for each team during each year. So each of these columns were used, and if the points allowed by the defense was higher and the defensive rank was lower, aka a higher number, we hypothesized that the maximum total DKP, aka the average fantasy points scored, would be higher, as well as the players would have a higher probability to play a really high scoring game. This is important because we can determine against what teams' defenses that certain positions would score their maximum points during that year and compare that for each team and the defensive rank. So for our first visualization, we used Insight 1, and this shows the plot as the defensive rank as the X values and the FPT over G minus total as the Y values, and this plot has a uniform distribution, so we can tell that the players are most likely to overplay their projection when the defensive ranking is closest to the median of 16 or within the range of approximately 10 to 22. For the second visualization, we used Insight 2 with the points allowed by the defense as the X values and the average fantasy points scored per game as the Y values. This plot is similar to a uniform distribution but is skewed to the right side, so we can tell from this graph that players tend to have an average higher fantasy points per game when the points allowed by the defense is roughly between 15 to 22.5. For the third visualization, we used Insight 4, which is the average fantasy points per game as the X values and the new expected value as the Y values. So this plot has a relatively linear correlation as seen above, but the X-axis goes up to 30 and the Y-axis only goes up to 20, which means that the actual fantasy points are roughly 5 to 10 points more than the new expected value that we created. So we can see that our new expected value has underprojected just slightly. So in summary, from this project, we learned a lot about sports analytics and how a lot of factors will go into each of the specific things we want to analyze. So we just did a simple dive into this, but as you can see, this project could be a lot more complicated from the data, and we didn't even do it with the defensive statistics yet as well, as there are a lot more to explore, as our new expected values were not as correct as we thought it would be, since there are a lot more factors that could go into it. Some challenges we faced were with the new expected values and also with clearing the NANs and cleaning up the data, as that took a long time, as we had to sort through the data and create a lot of if statements for each of the specific problems we had, and that created a lot of code and a lot of time in Phase 2, but after the data was completely cleaned, Phase 3 became a lot easier, and we are really glad we did that. Anyways, Thank you for your time.